Hi, good morning. Can you hear me? Yes. So today we start the main part of the course, which is the statement of the ADS-CFT correspondence, and then the first applications. So we start with the motivations. Well, we had the motivation last week, so we will make the statement, and then we will see the first matchings, and then more advanced applications during the week. So this was due to Maldacena. About 20 years ago. So we have the two ingredients, and the statement is that the following are equivalent. Which we also say dual. So we have, I will try to abbreviate this description. So we have type 2B string theory. In the background of ADS5 cross S5 with n units of Ramon-Ramon fluxes and radii of ADS5 equal radii of ADS5 and S5. And those equal to this 4 pi gs alpha prime square n to the 1/4. So that's the theory on one side. Closer. Let's try this way. A bit better. Thanks. So I carefully used just the type 2B language. So here all the variables are type 2B variables. There is the Ramon-Ramon flux. You see, I'm actually not talking about any branes here. And this is one of the first confusions that you might have. What's the role of the brane? There is no role of the brane in the duality. When I state the conjecture, on one side there is this part, and on the other side there will be the n equal 4 super Yang-Mills theory. Obviously in D equal 1 plus 3 dimensions. With so the Lagrangian is completely specified up to the gauge group, so I have to specify that, and the gauge group is SUN. So you will find in earlier papers, maybe even in Maldasena's paper, UN. That was the first form, but there was a subtlety, and actually it turns out it has to be SUN. I will not go into that. But in the large N, as we will study shortly, there is not much difference. It's basically the same at leading order in N. There is a gauge coupling of Yang-Mills, G Yang-Mills, and that is identified on that side with 4 pi gs. Okay. So in my previous lectures, all of these quantities, and these two theories appeared already. And I presented various motivations from the deep brain point of view, from the open closed string dualities point of view, for why there should be this. For example, this relation here was in a sense derived by doing the low energy limit on a word volume of empty brains and so on. But again, in the end, it is just a conjecture that these two theories are equivalent. There is no proof. And we will see that there are some pieces for this conjecture which are pieces of evidence which are quite obvious, but then it's very deep, and the consequences that it has, they go, I mean, it's a quite bold conjecture. It is not as obvious as it might seem from what we have discussed. So, in fact, the very same statement that I wrote there, string theory, makes this a very bold statement. Okay, so in fact, this is sometimes referred to as strong form of the conjecture. So this conjecture is supposed to be true for any values of n, alpha prime, gs, arbitrary large or small values. And because it's so bold and powerful, on the other hand, is practically impossible to prove or even to imagine how to prove. So with present days technology and even foreseeable future days technologies, we don't really, we can't really imagine of how to prove such conjecture. There is there is much more progress that we can do if we then consider some particular limit, which was done already initially by Maldacena and the followers. Right, so the idea is to consider a particular limit where we replace the string theory with the low energy limit, which is supergravity, which is one of the reasons why I went on for a bit, the initial 2 hours, introducing supergravity and the various properties that we are interested in. Okay, so the limit in the string theory side we have seen it already that the following limit was motivated. So this is a very large and very large. So this was the limit for validity of supergravity. As a good approximation, so for neglecting the corrections coming from alpha prime corrections, as well as the correction coming from string loops, so stringy corrections. So that was more or less explained on the supergravity side, and since we have now made this conjecture, we have to understand what do we mean, what is the implication for this limit on the field theory side. So if we can understand that, then we can make progress, because on the string theory side we can replace the hardly to compute with string theory on this background, and then consider supergravity on that background, and then we can do a lot of computations that I will start describing. So the next thing we will do is we will try to understand the implication of that limit in the field theory side. Okay, so it's like a small parenthesis that will take us for about 20 minutes or so talking about this topic. So we define, as it is customary, the so-called Tuft coupling, which is called traditionally lambda, and it's G square Young-Mills times n. Okay, so this is called Tuft coupling. And Okay, so we want to consider the limit of n very large, so n going to infinity, at fixed lambda. And this is called, this is called Tuft limit, or also simply large n limit. So the other thing that you want to understand is also the limit of, here it is, alpha prime going to 0, as well as GSN very large. So remember that in the gravity side we had the curvature was set by the dimensionful constant L square, 1 over L square. So the bigger the radii, the smaller the curvature. This is the limit in which supergravity is better and better. And going through the basic formula there, that's related to, in this variable lambda, 1 over lambda to the half alpha prime. So we can, if we consider an expansion coming from string theory, and for the moment we neglect loops, then an effective expansion would be an expansion in the power of alpha prime. And since we want to expand into a dimensionless constant, we can expand into alpha prime over L square. Okay, so there will be some first term, then alpha prime over L square square, etc., etc. So just a Taylor expansion in this dimensionless constant going to 0. And then from this equality here, we see that this is actually an expansion in lambda to the minus 1/2. Okay, so in fact, the expansion of they're just equivalent. The limit of alpha prime going to 0 and the limit of very large lambda are essentially the same limit. So that in the field theory side is going to be simply, well, we'll return to that in a second, but essentially we'll be taking this coupling constant to be very large. So once we reabsorb the n into G-Young Mills and we define this new coupling constant, we can talk about, instead of G-Young Mills, about lambda. But it is a little less obvious to understand what is the large n limit itself means, right? So for that, we have to go back to the work of Tuft, who was the one who explained that limit, defined and explained that limit. So let's now focus on the large n limit. This limit in the gravity side, it's trivial in the sense that we just take a large number of branes or large charge. So there is nothing to discuss. But in the field theory, it's not so trivial. So let's consider field theories that contain only adjoint fields, such as n equal 4 Super-Young Mills, which is the main example that we have. Say of UN. And I just told you that for the theory we need to consider SUN, but at the level of discounting, the modification is only slight, and it's subleading in n. So I will not do the SUN. So this is technically slightly more complicated. So let's consider for simplicity UN theories, and only with adjoints. This type of argument and counting can be extended also for other gauge groups and other representations. So the statement that we try to understand is that, so let me write the statement. The partition function, or generating functional, of the field theory, and therefore all the observable that follows from that, has an expansion of the following type. So here g for the moment is a positive integer, and then this has an expansion that has a power of n, this power of n, 2 minus 2 minus 2g, and then a function for each of these terms, a function that depends on this g, and it's a function of the coupling, the Tuft coupling. So, in particular, for n very large, the term that dominates is the term with g equals 0. And then, in this limit of n very large, the full partition function becomes n squared times a function of lambda, which, let's say, the function of lambda in principle can also be expanded in power series of lambda. So the different expansion. Now you consider an expansion in lambda. So you take C0 plus C1 lambda plus C square lambda square C2 lambda square, etc. Okay? But this expansion here actually makes sense only if you can take lambda small, right? So if you are in an arbitrary field theory and you want to play with that, you can consider the limit in which n is large and lambda is small, and therefore every observable that you have would be of this form. However, this is not the case here, right? Because we saw from there, so that second line there means that lambda is very large. Okay, so we will not actually be able to do this kind of expansion, and in fact the result at best in the context of ADS-CFT can be obtained in the opposite expansion of lambda very large, and then in powers of lambda to the minus half. So let's try to motivate this expansion here. So I made the statement and I want to motivate that statement. So you may have seen this already. The useful tool, actually the crucial tool for doing this, is to use notation of Tuft, which is the double line notation. Where we take our beloved Feynman diagrams, like for example, the propagator, and then which normally we attach some indices to be contracted if we are in some representation, adjoint representation of UN. And then we represent this as a double line going in opposite directions, okay? Indices I and J. And then the vertices, if we are just suppose in the usual Young-Mills theory, So there is no supersymmetry argument here. It's completely decoupled from supersymmetry. So we can take just Young-Mills theory, and then you replace that with this notation. The arrows always going in opposite directions. And in Young-Mills theory, we have the quartic vertex. So that is represented by this crossroad. Okay. Now, if we remember that the Young-Mills Lagrangian has a term which is f square, namely the covariant derivative of a square. And you remember that dA is dA plus G Young-Mills A. So all these are Zwiggles. Then we recover these Feynman diagrams and the associated power of the coupling constant in a second. So we get the kinetic term, the cubic interaction, which comes with the power of the Young-Mills coupling, and the quartic interaction, which comes with the square. Sorry. Sorry, I missed the square. You should have interrupted me. Okay, now it's better. This is the commutator A with A. Now, okay, so traditionally here we put G Young-Mills, and here we put G Young-Mills square. However, there is a more convenient, well, equivalent, but perhaps more convenient way to normalize the fields, which is to introduce a field which is rescaled by a factor of the Young-Mills coupling in the denominator. So just define a new variable, make a change of variable, and then the Young-Mills Lagrangian, we use a different color. So, well, okay. The Young-Mills Lagrangian will simply and nicely be proportional to 1 over G Young-Mills square with no other coupling. Okay, in this normalization. And instead of 1 over G Young-Mills square, I can introduce the Tuft coupling, just writing this in this way. So the Tuft coupling sits in front of everything here nicely. And moreover, when we now do Feynman diagrams, we can replace every Feynman diagram by one analogous equivalent one written in this double line notation. And then from this double line notation, it becomes clear that for any loop, in double line notation, there is a factor of n. So this is kind of a slight modification of the set of Feynman rules that you normally have. And here there is a reinterpretation of the usual Feynman rules that once you write them in this notation, because for every loop it means that there is a trace that carries a trace over n, you get a factor of n. So then we can start, as usual, to convince ourselves that some combinatorial formula like that is valid. We look at some example, and then from there we can extrapolate the validity of the form of the expression. So this is similar computation when you do Feynman diagrams, and there are certain relation with the dimension of the coupling constant and so on. So, for example, let's consider this vacuum diagram, which is one of the simplest thing that you can draw. So the vacuum diagram, if you rewrite this in double line notation, becomes this simple kind of a stop signal or something. And then we can count, first of all, we can count the loops. The loops are 1, 2, and 3. So there are 3 loops, which implies n cube. And moreover, there are 3 propagators, 1, 2, and 3. You can also see them from here, 1, 2, and 3. So we go back to here, and we see that to every propagator, now there is associated a factor of 1 over n over lambda, right? Because the propagator is given by the inverse of the kinetic term. So you get the inverse here. So there are 3 propagators, which gives a power of lambda over n cube. And then there are 2 cubic vertices. In fact, cubic or quartic in this notation, they have the same strength. So 2 vertices, in this case, they were cubic anyway, and that gives n over lambda to the power square. Okay. So in the end, if you put these factors together, we get, well, let me not repeat the algebra, we get n squared times lambda, which is also equal to n cube g square Young Mills, if you prefer. Let's quickly do another one. So another one that you could do, and this is of a different kind. That's why I'm doing both. Okay, so now here you have to pay attention while I draw that, because otherwise you get confused. So here I'm crossing this up. I'm not touching this here, so I'm doing kind of this and then jumping here. So this is in the middle is not a vertex. And then if I draw that in this notation, I have to do it a bit more carefully. So this is equal to, oh gosh, circle, and then this goes here, this goes here, this goes here. Okay, so here it becomes more evident that they're not touching in the middle. We do the counting, and we see that we get, well, the loops are now 2. One is this external one, and the one internal you can just throw out ever leaving the surface, right? So it's just one single line when you imagine that you have to go in the middle. So there are 2 loops. Well, let's write them here. You get n squared from the loops. The propagators are 6. So you get lambda over n to the 6th. And the vertices are 1, 2, 3, 4. So you get n over lambda to the 4. Yeah. So in the end, this is n to the 0. The factors of n cancel, times lambda squared. Let's go here. So if you think for a second what we have been doing when we do this counting, then you realize that we have been doing something very simple in terms of combinatorics. We have been putting L factors of loops for the loops. So let's call it E equal loops. Sorry, L equal loops. If I call E the number of propagators, and V the number of vertices, the formula is here. It's just putting this generically, these numbers. So you get lambda over n times number of propagators and n over lambda times number of vertices. But then if I write it in this notation, which is suggestive, then by collecting the terms of n and of lambda, I get n to the L plus V minus E and times lambda to the V plus E minus V plus E. And those of you who are good at geometry would recognize this formula here as something reminiscent of an Euler characteristic. And this is in fact an Euler characteristic of a surface. So let's write this and just comment. By the way, since this is an Euler characteristic, then for a closed surface, this is known to take the following form. Okay, so this explains already the appearance of this factor 2 minus 2g, right, where g is the genus of the surface. Right? And the genus is the number of handles, right? So the sphere has no handles, the torus has one, and so on. The more handles you have, the higher is the genus, and the more negative becomes the other characteristic. So what is exactly the surface that I'm talking about here? So you can see, for example, in this case, if you rewrite in that formula, this has chi equal to 2, which means that g was equal to 0. And the reason is that you can draw this diagram on a sphere, actually. So you have to consider the surface in which you can draw the diagram in double line notation, the compact closed surface, right? So you can take a sphere, a balloon, and just draw that, and you will find that it works. On the other hand, just to think of something which is different, this case here, you cannot draw on a sphere, because you can see that this one goes underneath. So this is called a planar diagram, because it can also be drawn in a plane, whereas this one, it cannot be drawn in a plane. I mean, it can be drawn by just at the expense of having to imagine that there is something that goes under. But really, you have to come off the plane. So this is a non-planar. So this is a planar diagram, and this is a non-planar diagram. In fact, this has a characteristic 0, so this can be drawn on a torus. So the limit, the Lagrangian limit, the strictly n to infinity limit, in which in this expansion here all the terms of higher genus are neglected, is also called the planar limit for this reason, right? Where we consider only the diagrams that can be drawn on a plane or on a sphere equivalently. Very good. So So then we understand what is the limit that we are supposed to be doing in the field theory. It's a large N or planar limit or Tuft limit. And moreover, once this is done, we are not free to consider some expansion like that, but we also have to do the large lambda limit. So we are at strong coupling even in the Tuft coupling. How we count the vertices? It's just, well, they're the same as here. So there's a one vertex here, right? One here, and one here. The line that goes underneath is not a vertex exactly like here. It's just a continuous line. This was supposed to be a 4, yes? Yeah. This was a 4. Okay. Yeah. So the weak form of the Maldassana conjecture then involves these two entries, which I wrote at the very beginning, entry number 1 and entry number 2. And then in addition, we want to be in the limit of large N, which is the planar limit in the field theory, and of large Tuft coupling, which is the limit also which allows us to be in the supergravity regime on the other side. Okay, so now that was essentially the statement of the correspondence and the regime of its validity, just by following the outline that I put on the web page. And the next thing that we want to do is to illustrate, well, this is what we say normally, that we do checks of this correspondence, right? So since it's a conjecture, either we check it or we use it to make predictions. Those are the two things that we can do. So it depends on your taste, really, what is that you want to do. You want to check something that you can compute on both sides, or you want to compute something that you can compute only on one side and then predict for the other. That is ultimately the rule of the game. We will clearly here begin with some obvious checks, and then we'll move on to explain in what sense there is also some predictive power. So the first check that we want to do is that of the matching of symmetries. So when you have two things and you want to claim that they are the same, they better have the same symmetries, right? Otherwise, what you are saying is completely wrong. Well, the symmetries sometimes can be manifest or they can be not so manifest. But in any case, at the end of the day, the complete symmetries must agree on the two sides. So let's recall a fact that we have already seen and just essentially recap on this part. So let's just write one set of symmetries and then say what they correspond to on the two sides. So we have seen that, okay, so this forms, first of all, a superalgebra. Which has a name which I can give now. Last time I didn't remember. SU2, 2/4. And what this means is exactly the thing above. There is this bosonic part of the algebra, and then there are 32 supercharges, and the complete commutation relation close into superalgebra, which is denoted by that. And here, this 4, we see that actually in the n equal 4 side really corresponds to the R symmetry of the theory. So in the n equal 4 side, we have that SO 2,4 is the conformal group. Which I reminded you is an extension of the Poincare group. And I'm sure that this week you will hear a lot about that. And SU4, which is the compact part of the isometry, which is an R symmetry in the n equal 4 side, and maximal SUSY. So the maximal amount of supersymmetry allowed by the dimension. On this side, on the ADS5 cross S5, this part is the so this is the isometry of ADS5. The second line is the isometry of S5, and maximal SUSY just becomes maximal SUSY here. Both sides, they have the maximal amount of supersymmetry here in terms of supergravity solution, and here in terms of Lagrangian of a field theory in 4 dimensions. So, okay, so there wasn't much to say because we set up the stage last time, and indeed the two set of symmetries match. In order for these symmetries to match, we don't really have to talk about the limits or particular things about n being large or small, etc. They just match on the two sides. One remark to be made, though, is that this is a symmetry which is just a classical symmetry. It's an isometry in terms of Killing vectors and so on of a background, whereas here the conformal group, as we know, it's something which emerges from a quantum computation. So it really has to do with the fact that the theory is conformal exactly. So there is some quantum statement here on this side. That will be a typical situation that in this limit of the supergravity approximation, quantum properties of the field theory are dual or equivalent to some classical properties of the supergravity background. It's a typical situation. Let me make some quick remark on this before we move on. So, a simple, at least conceptually, and if I have time, I hope to say much more about this idea. A simple extension of the ADS5 cross S5 duality is to keep ADS5 and replace S5 with some other manifold, say M5. So if we can do that, and I anticipate that we can, then on the field theory side, because ADS5 has still isometry SO2,4, we will still have a conformal theory, and depending on the properties of this manifold that is supposed to be replaced the 5 sphere, we would have different properties for the field theory, which is still conformal, but for example, typically we have a not maximal supersymmetry, so it may have a minimal supersymmetry or even no supersymmetry at all if the background does not preserve any supersymmetry. And then in general, the properties of this manifold, for example, if there are other isometries, they will translate into symmetries in the field theory. So this is a general rule that the internal geometry captures properties of the field theory, whereas, as we will see, the ADS5 part is the universal part that concern all the conformal field theories, Therefore, essentially, any computation that we do in ADS5 would be essentially applicable to any conformal field theory with the holographic dual. So a rich set of these kind of manifolds is called Sasaki-Einstein. Just throw this word, and if I have time, I will talk about that on Thursday, the last lecture. If I don't have time and I am around, feel free to ask me about that. However, apart from the symmetries, we would like, it would be nice, well, we would hope that the conjecture contains more information, right? So it cannot be that we conjecture, or Maldacena conjecture this duality just because the symmetry is matched, and it cannot be that because the symmetry is matched, then the conjecture it's true and that's the end of it. So we would like really to have a matching or a correspondence, let me say this for the moment in loosely speaking, of the physics. So the physics in the bulk should be equal, well, this is an equal sign, just rotated, to the physics in the boundary. This is a little bit vague, but it is actually a very profound statement. So, since the conjecture postulates that these two theories are equivalent, then this statement must be true. And in order to be useful, we want to make this statement precise, right? So we really want to say that any computation that one does on one side has a counterpart computation that one can do in principle on the other side. And if one were able to compute the same thing on both sides, then they should always agree. As I already said, sometimes these two computations independently can be done. And in all cases that have been done so far, which are millions by now, they agree. And in some cases, it's only possible to compute on one side, and therefore one gets some prediction for the other side. But in order to make comparison, first of all, as in any comparison, we should declare what are we going to compare. Right? So I should really try and begin to explain what do I really mean by physics. Right? It's easy to say physics, but one should say what do you mean by physics? The computation of what? What are the objects that you are going to consider? So let's go into the details. Let's just start from basics. What are the main objects that characterize our theories? Well, what are they? In the ADS part, they are the fields of the supergravity Lagrangian. Right? What do we have? We have the metric, we have some scalars, etc. So these fields. And because we are in ADS space, which is a non-compact space, we have to give some boundary conditions for them. So here I'm taking now the perspective for just short for a short while of an effective Lagrangian in ADS. So I'm for the moment forgetting that I'm coming from 10 dimensions and just taking the perspective that I have some Lagrangian which has ADS as a solution, as background, and then there are some other fields, and I will talk about where these fields come from because that's important from the string theory perspective. But for the moment I say that there is a bunch of fields in addition to the metric, right? So you can take as an example your preferred gauge supergravity in 5 dimensions, for example. And on the CFT side, what do we have? Well, for example, to be specific in the example of n equal 4 super-Yang-Mills, we have a gauge boson, we have 6 scalars, and we have 4 fermions, all transforming in the adjoint of UN or SUN, to be specific, right? If it was some other dimension, some other field theory, there would be some other gauge boson, some other matter content. Well, the point is that these objects here are intrinsically not good physical observables because they are not gauge invariant. So I am perhaps saying something which is obvious to most of you, but in this comparison which I'm about to set up, I can't really compare fields on this side with fields on this side. That doesn't make any sense, right? Because these fields here don't know anything about the gauge degrees of freedom. I mean, just there is nothing with gauge indices, just trivially. Okay, so not gauge invariant, therefore not physical. I should say not physical observable. It doesn't mean that we have to throw them in the bin, right? But rather we have to extract from them something which is physical and observable. That's probably going to go down as the most important, profound statement in my lectures. I'm joking. Right, so we must assemble these fields here, or whatever fields that are the fundamental fields of a given quantum field theory, at least in gauge invariant operator. Right? So they will be composite operators in the sense that they're made out of more fields. For example, that's a nice gauge invariant operator. In fact, not casually, it appears in the Lagrangian. There are other things which don't appear in the Lagrangian, but still they're gauge invariant, like, for example, trace of a number of arbitrary number of scalars, which are again in the adjoint, so I can put them in the trace. In fact, here I can have an arbitrary number, but let me stop here at 3. I'm just making examples. Or even mixed things with f mu nu, and phi. Right? So I'm taking advantage here of the fact that all my fields here are transforming in the adjoint, so I can just stick them in a trace, multiply together, and take the trace at the end. Now, I won't give any name to these operators, right? There will be many more, infinitely many that you can construct. So in principle, now that you have formed gauge invariant operators, there is a chance that you can relate them in some way yet to be determined to the fields here in the supergravity side. However, in fact, not all of these operators turns out they can be represented by the field in the supergravity side. First of all, we have to say now a bit more precisely what these scalars, etc. means, because as we want to always from string theory, so if we are considering an effective 5-dimensional theory in which the supergravity lives, then we have to derive this effective 5-dimensional theory from the 10-dimensional theory. That means that there is a further truncation. There is one truncation that you have done far in the past, that you throw away all the stringy modes, and you're left with the type 2b supergravity modes. But then if you want to go from 10 to 5, then you have to reduce further down. And that is the process of Kaluza-Klein reduction. So I have to explain a little bit of this Kaluza-Klein reduction, some main features. And once this is explained, then I can say a bit more which of these fields will be possibly related to a subset of all the possible gauge invariant operators that you can construct. So the statement is that of all the possible gauge invariant operators, only a subset, which may be infinite, can be represented by fields which appear in the supergravity approximation. And many of them, a large piece of them, will not be represented by this. So I want to specify what are the fields that appear here and what are the corresponding operators that can be dual. And this can be made quite precise. So let's do that. So this is obviously not a lecture on Kaluza-Klein reduction, so I will not go into the details of that. But hopefully I can give you the important conceptual points that characterize this procedure. So we have to, okay, let's look at Kaluza-Klein spectrum. And this will be done with, in mind, type 2b. But the statement which I'm going to make are quite generic. On ADS5 versus 5. And the 5 goes down. So I hope that you may have heard this at least before this idea, but otherwise I will repeat it again. So you have a theory in 10 dimensions, which is type 2b, and then you want to consider some fields which are reduced on the complex part of the space, the S5, and then give rise to some effective fields in the ADS5 part. So to set this up, we consider two sets of coordinates. Let's say coordinate x generically on ADS5, and let's say coordinate y with some indices, which here I'm not writing, on S5. So the coordinates on ADS5 could be one of your preferred matrix in coordinate system where I wrote the matrix. And the coordinate on S5 could be some polar coordinates of some sort. Then a generic field, and in fact this formula becomes almost exact if my generic field is the dilaton, but otherwise I would have to put some indices, which here I'm not putting. So this generic field phi could be one of the Ramon-Ramon fields or the matrix itself. That in 10 dimensions depends on all the coordinates, then is expanded in some sum over some basis of harmonics, spherical harmonics on S5. So that's the structure of the expansion. Yeah. Okay. So these are now some reduced functions in that live only in the ADS part, and these were, well, these are by construction spherical harmonics on S5. So if you don't know what these are, don't worry, it's just the basis on which you can expand, which is exactly analogous to the spherical harmonics in lower dimensions, like on the two-sphere, or even more trivially, like the Fourier analysis in one dimension, where you take the circle, right? So that's just to write a formula that may be a little bit more familiar. So this is similar to when you expand a function phi of x and the variable tau, sum over n, phi of x, e to the I n tau over r, okay? So here x is some space, could be just a flat space, and tau parameterizes a circle or radius r. So you can do this Fourier transform, Fourier expansion of this function in terms of this basis of Fourier harmonics. And that's the analogous statement in higher dimensions, where these YNs are well known. You can find them, probably even plugging them in Mathematica or Wikipedia or whatever. So that's not the important part of the story. Perhaps I should mention that the structure of the spherical harmonics then depend on also on the index structure of these fields here. So there will be spherical harmonics for the scalars, but then different spherical harmonics for the vectors, for the fermions, for the spinors, and so on. Right? So this is just very schematic. This word generic means that I'm just hiding under the carpet a lot of details. Now, that's what we have to do in general. And then here I give you a kind of a summarized recipe for how to do how to perform a Kaluza-Klein, how to obtain a Kaluza-Klein spectrum in 5 steps. Okay. So let's see if I can write 5 steps and that explains everything. So step 1. So write every field of type 2B supergravity as, so again, generic field, phi circle plus delta phi. Okay, so this is the physics. The physics is that your generic field is written as a part which is a background and a part which is a fluctuation. So the background is known, and it's the part that solves the equations of motion. In particular, if, for example, you are taking ADS 5 cross S5, then if this was the metric, this would be the, for example, the metric on ADS 5 or on S5, depending which components you are considering. If you are taking ADS 5 cross S5, and here you consider the expansion of the P field, this would be 0. But the fluctuations is always different from 0. So it can fluctuate on top of 0 or on top of some background. Okay, so this is completely fixed by ADS 5 cross S5, and these are generic fluctuations that you have to write for every field. Step 2. So you have to plug these into the equation of motion, and then you have to linearize. Linearize around dot, which means that when you plug them in, because they are PDEs, they are highly nonlinear and complicated, but you linearize in delta phi, so you get linear equations, some complicated or whatever operator you're getting, but acting linearly on this fluctuation here. Okay, so this gives linear for delta phi's. So as you can see, as I explained that, it is completely trivial in principle what to do, and the only difficulty is to actually do it in practice. Then for that you can read the papers that have done it, but having in mind what is the logic, then it facilitates the reading. So in the third step, you have to do essentially this step here. You have to expand in harmonics. So what you're really expanding in harmonics is the fluctuation part. Obviously, the background part stays fixed as whatever it was, and then you're expanding this delta phi. Okay, so that's the third step. And finally, well, almost finally, you get a system of linear equations which are still coupled. Okay? So something, well, there are mixed terms. So the basis that you obtain from these expansions here, the delta phi that you get originally, may not diagonalize the system. So although it seems a little bit weird, but you may have to consider combination of metric components together with phi-form flux components to diagonalize the system. So the diagonal modes are not just modes which you can think in terms of some pure 10-dimensional field, but they are linear combinations. Okay, so with that in mind, also helps in making sense of the paper. So you have diagonalized the linear system. Again, this is not a problem. It's a linear system, so you know how to diagonalize. And it's really a system with finitely many degrees of freedom. Right? The number of fields that you obtain, it's finite, but then there is an infinite sum over the modes. And finally, well, I think at this point you probably know the last step. You have to compute. Okay, what do you have to compute in the last step? If you have done some linear algebra. Yes. Okay, thanks for the suggestion. So you have to compute the eigenvalues of the modes that have diagonalized the linear system, and that will give you the full spectrum. Now, as we have experience from quantum mechanics, the process of diagonalizing some linear operator in the end will give some eigenvalues which will be labeled by some invariant, by some Casimir operator of some symmetry. And what is the symmetry here? Now the symmetry here is SU2, 2/4. Okay, so the infinite set of eigenvalues will be labeled by some, I put here quote marks for obvious reason, quantum numbers. And will, moreover, organize into a reducible representation of the symmetry group, which is also a supergroup. So these modes, characterized by these eigenvalues, which are labeled by the Casimir of this supergroup, these are the fields. These modes are the fields in ADS. Right? And you get infinitely many of these fields. That's okay, actually, because we had to take to account for an infinite number of gauge invariant operators. So it's kind of good that we get infinitely many fields. But the story is not over yet. So we still have to understand on the field theory side which of those operators actually can correspond to these modes here. So now somehow the problem in the gravity side is concluded. So I've extracted, or I've discussed how in principle one can extract all the Kaluza-Klein spectrum of type 2b on ADS5 crosses 5. And by the way, this is done in a very nice paper of the 80s that you can read very easily by Kim, Romans, and Van Noven-Neutzen. And then we want to go back and understand whether, and if yes, how these modes here will correspond to a subset of the gauge invariant operators that you can construct in unequal Superpin-Yang-Mills. Is there any question on the Kaluza-Klein spectrum? Is the microphone working? Yeah. Okay. Just checking. Okay, let's go back to unequal 4 Yang-Mills now. Well, that's the essence of my lectures, going back and forward between different systems and showing that they are equivalent. So back in n equal 4 Superpin-Yang-Mills, the symmetry is still this one, and of course the representation, let's say, if you consider these gauge invariant operators, they will necessarily transform into some irreducible representation of the group itself, because all the fields that you put in transform into some representation, and therefore when you combine them together, then they repackage into an operator which itself transforms in some representation of the symmetry group. Now let's focus for a second on the conformal part. So part of the bosonic group there is so focus for now on SO 2,4, and this contains two subgroups, which are SO 1,1 and SO 1,3. So that's the good old Lorentz group, and this is the dilatation group. It's one-dimensional, and it's non-compact, so it's actually the dilatation. So let's say this is D and this is J mu nu. So we know how fields will transform on the Lorentz group, and this is essentially taken into account by the indices, so we don't have really to repeat that basic quantum field theory lessons. But maybe we should pause and discuss a little bit how the dilatation part of the symmetry acts on the fields and on the operators, although I'm sure that this discussion will be by far superseded by next discussion in the bootstrap lectures. But anyway, this is part of what I've prepared. So let's discuss how under D, first of all, space-time coordinates transform. So that's got rescaled by some some constant which I call W for some reason which I don't know really. So this is a constant. And then if I take an operator, which is a function of space-time, then this gets rescaled by W with some factor, W of X. Right. So this is the action on an operator of the conformal, sorry, of the dilatation generator of the full conformal group. And this delta is called scaling dimension of the operator O. And sometimes one puts this delta subscript to remind yourself that this transforms with this delta. So it's a simple exercise which is worth mentioning. To understand how the representations can be labeled by different deltas. And to do that, we have to remember, or rather perhaps quote, since maybe I have not written before, part of the commutation relations of the group, of the full conformal group, which involve dilatation commuting with the momentum given I p mu, and with the boost giving plus I k mu. Okay, so this is part of the full algebra, obviously, of SO2, 4. So I'm not considering here the supersymmetry part for this part of the exercise. And then okay, so these are the quantum, so this is the classical version of this transformation, and the quantum version you have to promote this operator to some operators acting on some acting linearly on these which are regarded as states, and then you write this as some D operator acting on the state O, giving in some conventions the eigenvalue delta. Okay, so that's the typical quantum form of the operator D acting on delta. And from this definition here, which is the basic definition which is equivalent to this one, telling us that the operator O has dimension delta, then it is simple to see that if you take D and you act on the operator P mu O, right? So you want to compute the scaling dimension of this operator P mu O. Then you do something that you have done many times in your quantum mechanics exercises. So you sum and subtract some terms, and you get D commutator with P mu acting on O minus P mu D acting on O. So that's a trivial identity. And then you use this commutation relation. Onto here you use that D acting on O gives minus I delta. So you do some trivial algebra, and you get the result that minus I delta plus 1 P mu is the output. Okay, so that means by definition that P mu acting on O has scaling dimension delta plus 1. So similarly, you find that K mu acting on O, I write this in a different language, has dimension delta minus 1. So P mu and delta and K mu, they act as raising and lowering operators as in the harmonic oscillator. And therefore, exactly as in the harmonic oscillator, because there is actually a lower bound, the harmonic oscillator were just the fact that you want the energy to have a lower bound. Here, unitarity forces imposes the fact that there must be a lower bound on the dimension delta of an operator, which depends on its spin, etc. But in any case, since there must be a lower bound, and since k mu acts as a lowering operator, then there must be a state with the smallest scaling dimension, which acts as the vacuum, right? When you act on with k mu on that state, then you get 0. And such operators, they're called chiral operators. So there is some operator O lowest, which is 0. And so this is analogous to the vacuum state in quantum mechanics for the harmonic oscillator. And such operators are called primary. Right. So then you can construct a particular representation associated to a given delta by taking a primary operator with a given delta and then acting repeatedly with p mu by raising the value of delta. So these are called descendants. Okay, so that is as far as the conformal part is concerned. But let's now also use supersymmetry and use the fact that we are in a supersymmetric theory. Primary operators. Now let's use supersymmetry. So if we have supersymmetry, in addition to the D, the P mu, the K mu, the Lorentz, etc., we have the supercharges, right? So we have some. I just generically denote them with some Qs. And, well, you can also look up what is the commutation relation of the supercharges with D. So that is found to be that they higher the dimension by 1/2. So in particular, delta of, say, Q of an operator with dimension delta is then delta plus 1/2. Now, in n equal 4, Superyan-Mills, there are 16 of these supercharges. So one can form, since you can have only one of the supercharge because it squares to, obviously it squares to 0, then you can have one of the various supercharges, and then in arbitrary position they would just differ by some sign. So I don't have to specify in which position. You have about 2 to the 16 different operator for any given initial theta. So in fact, you can see that these representations that are given, labeled by a certain primary operator, on which you can then act with a p mu and increase the dimension, scaling dimension by 1, or you can act with a supercharge, and that would increase the dimension by 1/2. They all be characterized by the same delta, and therefore they all form the same representation, which will be huge, which will have many different states. So generic representations that are called, for this reason, long, this slightly vague name, but they're called long. And well, okay, this may be just a matter of taste. One could say, well, and so what? If they're long, and let's live with that. Well, there is a more fundamental problem. It's not only that they're long, it's the fact that the dimension of this the scaling dimension associated to this representation in general is not a protected quantity. So in particular, it depends on lambda and n. Right. So for these representations, delta is not protected. So it could depend. So delta is a function of n and lambda, in principle. That doesn't sound very promising if we want to compare with the Kaluza-Klein spectrum, in which there is no n and there is no lambda. At best, n will be some trivial scaling overall. But definitely there is no lambda. And the reason is that in supergravity we are in the strict lambda infinite limit, strong coupling. So if there are operators in these representations whose dimension depends on lambda, then there is no hope that they can be matched to the Kaluza-Klein spectrum, right? So in order to improve the situation, we would like to find some condition, if it exists at all, such that the dimension of the operators is not anymore depending on lambda, and it's something which depends only as the spectrum on ADS5 crosses 5 on the Casimir of the representation, right? Depends on some quantum numbers. There's some integers that label, well, there will be, for example, the spin in ADS5, and there would be various angular momenta in the internal 5 sphere. So that's the last step that we want to do. And this is simple. It's similar to the idea of the primary operator, but it is a condition that now involves the supercharges themselves, right? So the idea is that if you start acting with some Qs, and at some point, hopefully much earlier than getting to the Q to the 16, you get 0, then this is a condition for a shortening of the representation. So if you get generically some combination of Qs that may be slightly complicated, so I will not write any example, that act on given primary operator. So if this is true, then theta is called, or O, I sometimes call it theta, O is called chiral primary. And if this happens, then by its own construction, the representation is shorter than the generic long one, because it has far less states. So these are called, again, with a slightly generic name, short representation. Is this a sign that we are close to finishing? Oh, no. Okay. Now, so the chiral primary operators are our main subject of interest. And not only they are short, they form short representation, but they also solve the other and worse problem, that the delta, it is not non-protected, but it is now a protected quantity. So it achieves exactly what we wanted to achieve. So delta is, for this kind of chiral primary operators, is uniquely fixed in terms of the R symmetry. Right? For n equal 4, which is the main subject that we're talking about, this is SU4. But in fact, these statements are more generally valid also in n equal 1 superconformal field theories. You can also have a notion of chiral primary operators in n equal 1 superconformal field theories, and also in that case, the scaling dimension of the chiral primary operators are fixed by the representation of the R symmetry. In that case, the R symmetry is U1, so it can be slightly less powerful. In this case, because it's SU4 and it's non-abelian, in fact, it is completely determined by some integers, right? So these are essentially, these are the charges which are integers, or R charges, which are integers. So these are exactly what I was referring to earlier as angular momenta on the S5. Yes?
Why is it not protected before and now it is?
Okay, that's a good question. The reason why it's not protected before is because they had no reason to be protected. The reason why it becomes protected now, it's in two steps. First, from that relation there, if you manipulate that enough, you will get a relation of the delta to these R charges. So that's the key. So a relation on the an equation that is obeyed by the operators implies an equation which is obeyed by the R charges. Yes, that equation implies this relation here, and then that's it, because then the R charges are completely fixed by the Casimir of SU4. In n equal 1 case, you'd have a similar statement that some combination is annihilated, gives a relation between delta and R charge. But then you have a kind of more interesting, richer story, because then in n equal 1 case, the R charges are not so simply determined by the symmetry. So there is some dynamics to be solved there further on, which has to do with the process of A maximization and so on. But once you get to this stage, you still have to determine R charges. And it happens that these R charges are not integer. In fact, there are some rather ugly numbers. So that's a different direction, and something which probably I will not have time to discuss, except some more comments in the last lecture. But for here, we are thinking about n equal 4, and therefore the R symmetry is SU4, and that fixes uniquely these numbers in terms of some integers, and we are done. So in fact, this is something I wanted to write next. So for n equal 4, these charges, these R charges, which I wrote here a bit vaguely, these are given. You can choose different bases. One possible basis is some Cartan of SO6 or equivalent to SU4. So these are Casimir's for SO2 square, let's say SO2 cube inside SO6. Okay. So if you view the symmetry of n equal 4 as SO6, then there is a Cartan subgroup, which is U1 cube or SO2 cube. And each of these has an integer associated, which is like an angular momentum in a plane. And this is called Q1, Q2, and Q3. And then if you fix these three integers, then you fix uniquely in the R charge, which in turn fixes the dimension of the operator if it's a chiral primary. Okay, I already made the remark about the R charges not being rational in general for n equal 1. So then we are back in business, because now we have operators which come in short representations, by the way, and which have a dimension which is fixed by some integers, and these integers are exactly given by the Casimir on SO6, and this is exactly what happened to the Kaluza-Klein spectrum on S5. So those numbers were fixed by the Casimir of SO6, which was the isometry of S5. So there are all the ingredients pointing to the fact that now these two sets of operators and fields are likely to match, and they actually do. So this was pointed out early after the Maldacena paper. Probably the first paper was the big Witten paper on the topic that had this pointed out this matching of spectra. So again, I stress the fact that now these dimensions do not depend on lambda, and therefore they can be matched to the gravity side. So let's look at some examples. So this is how it proceeded historically. So first of all, people looked at the few examples, and then shortly afterwards they checked, because they can be put in tables, and then when you check that all the tables on one side match with all the tables on the other side, you have shown that there is an infinite number of fields and operators that agree. So we will not do this thorough check, but we will just mention a few examples. So for example, on the field theory side, we have operators of the kind which I have already sketched, which involve a trace of scalars transforming in the adjoint. But then we have to do a little bit extra massage to that. We have to antisymmetrize these indices of SU6. So in fact, this representation is the totally symmetric and also has to be taken traceless. If it's not traceless, then it's not true that it's a short representation of SO6. So I wrote this because it's particularly simple to write, and because its scaling dimension is particularly simple. The scaling dimension is, in fact, turns out to be n. And in fact, also n has to be larger than 2, or larger or equal to 2. This is something that in the field theory side it's obvious. Let me try and tease you. Why it is obvious? Yes, because it has to be SUN. And in fact, retrospectively, this was one of the evidences that the gauge group has to be SUN, because on the Kaluza-Klein side, these modes actually do not exist for n equal 1. There is only this mode that exists for n equal 2 onwards. Okay, so that somehow was an evidence that the gauge group has to be SUN. Another example is acting with some sufficient number of supercharges, namely q to the 4th onto the previous ON plus 2, then gives trace of F mu nu, and again with these phi's in the symmetric. And now this has delta equal to n plus 4, and here n can be equal or larger than 0. Right? So for n equals 0, we get our nice kinetic term for the Lagrangian. Okay. So given these examples, and given the fact that they have this particularly simple dimension, we would like to try and attempt to identify the corresponding mode in the Kaluza-Klein spectrum in the ADS5 part. So I want to say, now I'll go back to the Kaluza-Klein part of the story, and I want to go a little bit more into the detail of how this computation is done on these eigenmodes. Now, the reason why I choose to present these two operators as examples is also the fact that they are scalars under the Lorentz group. Right? I could have operators which have Lorentz indices. I don't mind about that. Right? I only mind that I get gauge invariant operators, so they don't transform under gauge transformation. But they could have Lorentz indices. So now these are simple because they don't have any Lorentz index. Rather, the indices are contracted. So then it tells me immediately that I have to consider a scalar. So on the ADS5 part, those correspond to scalars. What are the scalars? Is it the dilaton? Well, no, because not necessarily, because these come from the reduction. So there could be various modes that you have diagonalized, you have mixed and disentangled, and you get a bunch of scalars. So if it's a scalar, in any case, and after you have diagonalized its linear operator, what you'll get in the end of the day is some Klein-Gordon operator acting on this mode. Now, this equation here is going to be our friend for the next few hours. It will come back and in various different sources. So the first question you are going to ask me, or maybe if you know the answer, you are not going to ask me, it's what this m square has to do with the delta on this side, right? So here there is some delta, which is an integer or some combination of integers, and here you have a mass. So what the hell? Now, first of all, this mass comes exactly from this reduction. So by itself, it's going to be given in terms of some Casimir of SO6. Second of all, the mass is not just equal to delta, but there is a formula which I'm going to first write, and then I'm going to prove it perhaps, actually almost certainly this afternoon. So the relation is that, so this is one of the famous and very general part of the dictionary between ADS and CFT, and it gives delta, or you can invert this if you want, in terms of the mass of the operator. And as always in these lectures, I will assume that my ADS has radius L square, or L, and this is the relation that you get. It is also worth mentioning that this is true in ADS5, whereas in ADS D+1 there is a slightly more general formula with factors of d. Let me write it. So, as I said, I will derive this formula, so don't panic about that. An interesting feature of this formula is that from here you can see that since the scaling dimension have to be at least real, in addition has to obey some unitarity bound, so it has to also satisfy some lowest bound, but in any case it has to be real. So it has to be real, therefore this entry here under the square root has to be positive, right? And so that puts a lower bound on the mass, which at first it's a bit puzzling because it's negative. Right? So in anti-de Sitter, the mass of a scalar can be tachyonic, or at least it has the mass that appears in this operator here can take a negative value, not too negative. This is the lowest negative value that it can take, but it is allowed. So this was studied also in the 80s, or maybe even before, by Bretinor and Friedman, and it's known as BF bound. So what I'm telling you is that something which is rather obvious from the field theory side, namely that delta has to be real, it matches to a condition which was discovered far before the ADS-CFT correspondence was even conceived by this gentleman here, and they found that actually for a scalar to be well defined in quantum mechanically in anti-de Sitter, its mass has to be larger than this number here, not just simply positive. So tachyons are allowed in the anti-de Sitter world, which is interesting. Let's put this up. So in order to derive that formula, which it's best done after lunch, when our energies are recharged, I will introduce what is called as the master formula of the ADS-CFT correspondence. So I will soon, in a few minutes, by the end of the lecture today, I will write the ADS-CFT master formula. Okay, so this is at least the way I refer to it in my papers. I'm not sure how people refer to that, but it's what captures, it's what makes really precise this very vague board that appeared some time ago, where I said the physics in the bulk has to be equal to the physics in the boundary. So actually, this formula here, which I'm about to write, exactly captures that statement and makes it precise and makes it into something which we can compute with. So this formula will answer, hopefully, at least it should answer, two questions. That may arise. So the first question is, what is the physical motivation to associate, pair somehow, a field phi in the bulk to gauge invariant operator, blah, 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 in the boundary. Okay, so here, some of you, or most of you, may have been puzzled or not satisfied by my comment that I take a Kaluza-Klein spectrum of fluctuations of fields in anti-de Sitter, and then I associate them to gauge invariant operators in the boundary. The reason which I gave so far is that, well, they kind of have the same. They have the same symmetries. They are labeled by the same Casimirs, and also they are both gauge invariant. So presumably they should match. But there should be some more physical motivation for doing such an association, right? And this formula is going to answer this question. The second question is that in a CFT, more generically, not just in superconformal field theories, but in conformal field theories in general, the observables are actually correlation functions of these gauge invariant operators. So when I give to you a gauge invariant operator, and I said that's the physical object, well, that's almost, it's not quite yet, because you have to form then correlation functions, and those are the physical observables in a conformal field theory. So these are here in some still vague but universal notation, correlation functions of arbitrary number of these gauge invariant operators, where in the simplest case you would have just one-point function, namely expectation values of operators, and then you have the two-point functions and so on. So since these are the observables of the conformal field theories, and since I am advertising the fact that the ADS-CFT correspondence maps the physics in the bulk to the physics in the boundary, and the physics in the boundary is captured by these guys, then I should be able to do some computation in the gravity side that computes exactly these field theory correlation functions. And this is the second question that this formula here is going to answer. So it's kind of a, I don't know in English, two pigeons with one stone, something like that. Now, the question is, are we ready for the, okay, we'll do that. We'll do an appetizer, master formula, and then we'll take it after the lunch. So I'll just give you an appetizer. I'm sure you don't need any appetizer by this time. So here we go. Z of the QFT is as a function of J is equal to should I give you this? Yeah, let's really give the simple version and not without any explanation. Z of string as a function of phi 0, where J is equal to phi 0. Now, to make this a little bit more interesting, I have to define what is ZQFT and what is Z string. Although actually you can kind of imagine what they are. So this is going to be the generating functional of correlation function in the field theory, where J is the source that allows me to compute correlation function by functional derivatives. And this is going to be the partition function of string theory, a rather mysterious object that no one really has computed, that depends on the boundary value of your fields that propagate in ADS. Okay, so with this scary remark, I leave you to go to lunch. I think it's about time.